Okay, it's moving already. So hello everyone, wherever you're logging from. Today I'm talking about methods that we use in strong field and attosecond physics, which is an area which is not really standard quantum chemistry, but there are some overlaps. And to start with, because I understand we have a broad audience, I'm going to talk about strong field physics, and I'm going to talk also about imaging and what are the challenges that appear when you're working in extreme conditions, such as in my field of research. And especially I'll try to give you an idea of what is new and what is important. Then I'm going to talk about orbits. Why do we care? Why are we so focused on orbits? And the things are that all the paradigms that exist in our field have been defined in terms of orbits, and they're very useful to describe these conditions that we'll look at. And I'm going to talk also about the old theory, which is not that old because it's still used quite a lot. And this is a strong field approximation. So I'm going to give you a broad overview of advantages, drawbacks, and modifications over the years, and then how people decided to go beyond. So novel orbit-based approaches that incorporate what we need to have. And this last bit is about our work. So I'm going to talk about one orbit-based approach that we have developed at UCL, which is the Coulomb Quantum-Orbit strong field approximation. Then this is going to be applied to photoelectron holography, and I'm going to give you a summary and an outlook. Okay, so let's motivate our talk. When I talk about strong fields, what do I mean? I mean intensities of 10 to the 14 watts per centimeter square or higher. So this is a timeline showing you focus intensity versus time. And what you can see is that here we're talking about things that are huge, that are extreme. So extreme that maybe in the future we're going to be able to polarize vacuum and have nonlinear QED. Nowadays, we are around here. And if you're wondering, shall I put my hand in front of it? Here, you should already stop much before. These intensities are really, really, really high. And one thing that also happens is that in my area, we're dealing with some of the shortest time scales in nature, which are hundreds of attoseconds. This is easy to see. If you get atomic distances, or you get 10 to the minus 10 meter divided by the speed of light, you see that that's more or less what you're going to get. And you can see again in this plot that everything else is here. And here we have pretty much electrodynamics in real time. And if we manage to control these and we manage to understand this can really revolutionize how we view physics. And for that reason, people have been looking at imaging of molecules, of solids, and you have always to start small. So you start with structural minima and single orbital picture, which is something very approximate, and this was done in the early 2000s. Then we'll move to try to reconstruct orbitals, but obviously, if you are dealing with a real molecule, the real thing, you need to take into consideration multi-electron effects and core dynamics, which is what has been happening in the past decade. And now solids are all the rage. So the work continues, and we need more and more and more sophisticated methods to deal with that. And the trends that we observe is that because you're dealing with complex targets, you need to take into consideration correlated multi-electron dynamics in very, very, very strong fields and under very short time scales. You're going to have also light-induced effects. You're going to have resonances, all sorts of things. And this is going to occur in larger systems. So, and these things are going to overlap. And the question is how we are going to treat this, especially because usually we talk a lot about continuum. So the continuum now is going to have a structure. And before, as I'm going to argue next, we had an unstructured continuum. And what is very important are orbits, as I said, and what changes. Normally, if you're dealing with intensities that are weak or relatively weak, you look at the time-dependent Schrödinger equation. Let's say this is the simplest case that you can have one electron in a field. So this is the atomic Hamiltonian. This is the coupling with the field. Normally, what happens is that if the field is weak, the laser field is much weaker than the atomic binding forces, so you can treat the field as a perturbation, and that's how people are used to seeing an external field, something that excites or de-excites the system. And for strong fields, people started to observe trouble already in the 1980s, 1990s, because the stark shifts started to get closer to the photo energy, so there were huge distortions and there were discrepancies. Now, if you come to a situation in which laser fields are comparable to the atomic binding forces, then perturbation theory is going to break down because these things here, they're comparable. So how do you deal with that? And there have been approaches that do exist since the 1990s. And orbits have been played a huge role in the sense that they describe the main features that you find in photoelectron or high harmonic spectra. And the phenomena that occur, they are described by laser-induced recollision or recombination. So you pull one electron out, it reaches the continuum either via tunneling or multi-photonization. This electron propagates, gets a lot of energy from the field, is driven back, and then if you recombine, all that kinetic energy is transformed into high frequency radiation, so you have high harmonic generation. If you rescatter elastically, you're going to have very high energy photoelectrons, and that's what we call rescattered above threshold ionization. If you collide inelastically, you give some energy to the core, and then you may ionize other electrons. So these things, they happen at very specific times because tunnel ionization happens when the field is close to its maximum. Recollision, recombination happens when the field is close to a crossing. And this means that the field is dictating these time scales, is dictating the phases that the system picks up, and is dictating also the dynamics. So because you have a fraction of something that is a few femtoseconds, which is a cycle of the field, you are in the attosecond region, hundreds of attoseconds. And one thing that is really, really important is quantum interference, because when you're measuring things and when there are in principle several pathways that this driven electron can take to reach the detector with the same energy, or for it to emit light with a certain energy, then these things are going to interfere quantum mechanically. So quantum interference needs to be taken into consideration. So that's why I'm focusing here on quantum and semi-classical strong field approaches, because many people have used also classical approaches to describe things. But it's important to bear in mind that quantum interference plays a huge role, and we're going to take this into consideration. So let me start with a history lesson. Let me talk about the old theory, which is a strong field approximation. And the key idea is you have here something that you cannot solve analytically, which is this Hamiltonian of an electron in a field. But you can solve, supposedly, this, even if you cannot solve analytically, it's easier to solve. So you neglect the laser field when the electron is bound. You have field-free bound states. And you also neglect the ionic potential when the field is in the continuum. This you can solve. This has in fact a name. This is a Gordon-Volkov Hamiltonian. And you assume that the continuum is approximated by Volkov state, which are field-dressed plane waves. So you have a field-dressed plane wave continuum, which you can also solve analytically, and you neglect the internal structure. So if you want to understand how this is built, let's consider that you have the time evolution operator for the full system. So here you have everything. You have field and you have atom, and you have a final state psi t, an initial state psi t dash, a time evolution operator taking it from t dash to t. And you can write this in terms of an integral equation. Here I can choose A and B as time-dependent Hamiltonians, and I have uj, where j is A and B, which are time evolution operators associated with those Hamiltonians. And this is in fact how we build perturbation theory. Normally, the one that I said doesn't work. And at the moment, this is still exact. This is an integral equation. It's just a way of writing the Schrödinger equation in integral form. And if you iterate it, so that's when it's tricky. You need to be careful and you need to see what is your perturbation. Because when you iterate this series, you get a perturbative expansion. And you get also time ordering, as you can see this. And what we know from our quantum mechanics courses, like fourth year, is the weak field perturbation theory. So you have HA is the full Hamiltonian, HB is the field-free Hamiltonian, and the perturbation is going to be this guy, which is the interaction with the field. So why not pick, if you have a huge field, why not go for the opposite, pick up the Coulomb potential as the perturbation? And this is what we know as Gordon-Volkov series. Now, our problem is different, because our problem is that you have comparable field and potential. So neither is much stronger than the other. So at the end of the day, you need to cook up something which is neither the standard perturbation theory nor the Gordon-Volkov series. So, and again, as I mentioned, this you can solve analytically, the Gordon-Volkov Hamiltonian. And here, this is perturbative with regard to the potential, non-perturbative with regard to the field. So you always have to bear in mind what your perturbation is. Okay, so what you do with the strong field approximation, which clings kind of insane, but it works, is you mix the two perturbative series. So here, when you had the integral equation for the full time evolution operator, you replace it by the Gordon-Volkov time evolution operator, which means that U0 is associated with the field-free Hamiltonian. This is associated with the Gordon-Volkov Hamiltonian, and we have still this interaction here. But because we made this assumption, it's not a perturbation with regard to the field. We have constructed, and we can keep on iterating, and you construct a series which has a modified basis. So formally, we have perturbation theory, but it's something that is non-standard because you have modified the basis to include field dressing. And the physical idea is the one that I started with at the very beginning, that you neglect the field when the electron is bound, and you neglect the potential when the electron is free. And also, because you make this assumption here, if you apply this to an initial bound state psi naught, you're going to see that you end up with a state that is going to be a bound and continuous superposition. So you are going to neglect excitations and things involving excited states. And for strong fields, at least for a long time, what is really important for us is bound states and the continuum. So this actually worked very well to explain things. And to give you an example, I'm going to bring some applications. So If you just consider that first term in perturbation theory that I have shown you and use the modified basis, and you want to compute strong field ionization, so you take the system from a bound state to a continuum state, you are going to have what we call Keldysh-Feisel-Ries theory, and they were developed by these three people independently. So this is Keldysh, this is Feisel, and this is Ries. The difference is the gauge they use, and I mean, I'm not going to go into details here, but one of the big problems with the strong field approximation is that it's not gauging variant, and there have been real battles and fights what gauge is the best, which is a bit insane because, I mean, if you have something describing a physical system, it shouldn't depend on the gauge, but unfortunately, when you do this mixing, it does. And these people, they have been discussing this for ages, and they made seminal contributions to the field. And one application which is also quite nice is above threshold ionization. You can see this is something that is still being used nowadays. Strong field approximation is old, but it's very useful. For instance, this is a computation in which people looked at interference carpets. So this is a photoelectron momentum distribution from experiments and from ab initio computations. And here you have what you get from the strong field approximation. And what here we assume is that we have photoelectrons that are being ripped out of the system via tunneling, and they reach the detector without further interaction. So these are what we call direct electrons. And if you look at the transition amplitude, once you write it in a nice way in momentum space, you see that it has something here which contains the ionization potential. You have something that looks like a semi-classical action. You have here something that is associated with this field, which is the interaction we have considered. Here you can see its length gauge. And here you have something that is going to give you information about the bound state of the system, which is relating to this initial state. And people have looked at it a lot. But you see, this has a form, if you want, of a path integral, but with a lot of approximations, because you have here semi-classical action, and you have some initial prefactor, and you have here some time integral upon this ionization time. So let's have a look at how to improve it, because we talked about these laser-induced rescattering processes. Okay, so one thing that you can do is take the other term. And this was done in the late 90s. So you can see that here you have included one rescattering with the core. So this is what we call, we're going to use to calculate rescattered ATI and also harmonics. And this is like a Born series, you see, but has, instead of having a plane wave, has a field-addressed plane wave. So we say also that the strong field approximation is a Bom-type approach because of that. And if you look, this is pretty much the difference. You can write this in a much more compact form if you compute the matrix element from an initial bound state to a Volkov state by doing some tricks with green functions. But effectively, that's what you find. And this is nice also historically, and not only historically, because it started to explain features people couldn't get with perturbation theory. For instance, in above threshold ionization, there was a region in which the electrons had comparable, photoelectron had comparable strength, the peaks. And suddenly then there was a drop in yield. And this is what we call the plateau. And in the 1990s, people just didn't believe it exists, and it's something that the strong field approximation explains. And the cutoff is the maximum energy this photoelectron would have upon return before recolliding with the core, or the energy that it would occur after recolliding with the core and reaching the detector, in fact. So it explains this plateau, it explains this cutoff, And it explains this reach, which is the maximum photoelectron energy the electron can acquire in the continuum. Here you have a momentum map, which is actually also done in the late 90s, 2008. And you can see that this reach is very typical for rescattering, and is explained by looking at this kind of constraint that strong field approximation helps to define. Also, one thing that you could do is consider that the final state is a bound state. So instead of taking it all the way to a continuum state, use that time evolution operator that you have derived and consider that you have recombination, or compute the time-dependent dipole moment using the strong field approximation wave function, and you're going to get that high harmonic emission in which you have shown this near or mid infrared light, and you got harmonics up to the XUV range. And one thing is, because this process happens at very particular times, what also happens is that you can group that you have phases that associated with these high harmonics, and you can group harmonics and create attosecond pulses. And attosecond pulses were proposed in the late 1990s, and they have become hugely important. And they are used for metrology, they're using for controlling systems. There's even a competition who gets the shortest attosecond pulse. And if you are interested in that, you can have a look at this review. It is very enlightening from the point of view of what exists. And another very important tool that exists is the if you would use the strong field approximation in conjunction with the steepest descent method, is that you can go back to this picture of orbits. So here what we have is this ray scattered above threshold ionization transitional amplitude, but written nicely in momentum space and considering all the integrals that you have. So again, you have some kind of action, but you see that you have this phase from ionization, but you have another phase difference, which is from T dash to T, and this is associated with propagation in the continuum. And then you have from T to infinity, which is something that is associated with rescattering and then propagation afterwards. And you have these two interactions here. This one happened upon ionization. This one is when you had this rescattering. And if you apply the steepest descent method, so you're going to seek variables such that the action, which is this thing here, is stationary. The first expression that you get in terms of the ionization time T dash gives you energy conservation. And you can see that this here cannot have real solutions. So you're going to have to go to the complex plane. This gives you complex solutions. Then if you do this with regard to the intermediate momentum K, you see that it is constrained in such a way that the electron is obliged to come back. Then if you differentiate the action with regard to the rescattering time T, you get energy conservation at the time of rescattering. So all those things that were postulated classically and hypothetically, they come out of this theory, which is something that is actually very nice, because also you have quantum interference and you have tunneling. But you need to be careful. You are in the complex plane. You can solve this using asymptotic expansion. So you could have a sum over orbits. That's how this would look. But what you are going to have is you're going to have pairs of orbits that are going to coalesce at that energy, which we call the cutoff. And there are several cutoffs. That one, which I showed you, is like just the most external one. There are several minima and maxima for the, we are interested here in the maxima for the energy. And what you see is that these two shadows that occur in pairs, they're going to start to coalesce, which means also that you are going to need a uniform asymptotic expansion if you would like to model this. And this was an obstacle for a long time, how to treat this problem, because then need to have an asymptotic expansion that is valid over all values of the energy for the harmonics and for the photoelectrons. So here, these cusps that you can see, these caustics, they are because the asymptotic expansion started to break down. You couldn't treat them anymore individually, like what is written here. So you need to consider pairs of orbits collectively, and this is the red line. You see, it works pretty well. And if you integrate that transition amplitude numerically, you see that the difference is like negligible. It works really, 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 really well. And the old theory has been used for many things, namely, you can change it to incorporate electron-electron correlation, excitation. In fact, these results here, for instance, they were kind of old, but these that we had, they are more recent. And you could see that we described, in fact, quantum interference. These are correlated to electron plots in which we model this non-sequential harmonization process. Here you have some direct process. Here you have some kind of excitation process. Here you have some experiments with pulses, and we could identify quantum interference patterns there. Here, people recently have done some work to move towards solids. So how can you change the strong field approximation to consider solids? What would be your continuum? What would be your ground state? What are the assumptions that you make? How do you put dispersion relations? And you have to consider currents, not a single electron. So this has been done by Van and Brabeck in 2017. A lot of people have been using this and improving it. Also tailored fields. So this is a big, big, big area. And the strong field approximation has been modified and is used. This is amazing. These are bicircular fields of several shapes, and you can see all these figures. These are electron momentum distributions, which were calculated in Sarajevo by Milosevic and his groups. So really beautiful. And molecules as well, simple ones. These are some computations that we have done for N2 beyond the single active orbital approximation, because this needs to be done. And we found cutoffs and features associated with different orbitals that we could extract from our high harmonic spectra. This is harmonic spectra as a function of alignment angles. So just to make the case, this is very useful. This is very nice. If you're more interested, have a look at these reviews. You can see some of them are fairly recent. And, well, it's good, but it does have some drawbacks, and we are going to have a look at them. Advantage is this is powerful, super powerful, semi-analytical. And so super powerful, I mean, in principle, you could use this for large systems without having to fear the exponential wall. And it's powerful because it's semi-analytic. You can push things analytically by using Hamiltonians that you can solve analytically to a big extent. You have this intuitive orbit-based interpretation, which is also very positive. You have quantum interference and you have tunneling. And there are some powerful concepts there, which is factorization of tunneling, recombination, and propagation. So this means that you can factorize a process in general, or in principle, depends, of course, the situation you are dealing with, in tunneling, propagation, recombination, and these are factors that are in your transitional amplitude. Now, nothing is perfect, and the fact that you made all these assumptions and you eliminated the residual binding potentials means that although your field is very strong, the potential is there, and you're going to pay a price. Also, if you're ripping off one electron, the system is going to rearrange itself. So you are expecting that you're going to have a relaxation, you're going to have excitation, you could have whole migration, you know, all sorts of things happening. This, as I mentioned, is a big deal. And you would actually like to have a theory that doesn't break the gauge invariance in the first place, instead of fighting over which gauge is better. Sometimes you have to fight, though, and but it's important to bear this in mind. And there's also something that is fondly known as the curse of the displaced atom. Because if you have your exact Hamiltonian, the bound state and the continuum, they are orthogonal. But as soon as you replace your continuum by plane waves, be them dressed or not, they are going to be not orthogonal to the bound states. And you can kill this or throw this under the rug if you put the atom in the origin. But if you have a system which is spatially extended, or even a small diatomic molecule, you're going to be in trouble, and you need to be really careful about what you're doing. So because of that, people decided to go on beyond, including ourselves. And the first thing that you do is you say, okay, these orbits work so well, so let's use the fact that the SFA is factorizable, and let's try to introduce the distortion caused by the potential in the continuum states. So instead of using a Volkov wave as an asymptotic state, let's consider that you have a Coulomb distorted state, or let's consider that you use a cross-section that is exact and use the fact that you can factorize it and you can place it in recombination part or somewhere else. And this has been done by a lot of groups. So this one was done in Kansas. This is quantitative rescattering theory. This was pretty much in Vienna and Buenos Aires together. So Coulomb Volkov approximation. And this one, Sarajevo and Berlin, by Wilhelm Becker and Dejan Milosevic and their groups. This is more rigorous, but it's the same principle. They just went one term more in the field dress-born series, and then they made additional approximations. And the key idea is that these orbits are not touched upon, because, I mean, you have to deal with them with further challenges. So this is to give you an idea. I'm just picking up one of them. And for instance, in Coulomb Volkov approximation, an assumption that you make is that the final Gordon Volkov states are replaced by Coulomb Volkov states. You also assume that the laser is going to distort the Coulomb continuum adiabatically, and because of that, you can use that factorization that I was talking about. So you are going to use a wave function, which is associated with this state, which is the Coulomb Volkov state, and you have some kind of Coulomb factors that you put in the Gordon Volkov wave function to incorporate this distortion. And this kind of works if the Coulomb potential is not influencing the continuum dynamics too much. For instance, here in this case, all the distortion that you have, because you have a high frequency, and the distortion that you have is coming from close to your final Coulomb state. The continuum dynamics is not being changed a lot. So you can see, for instance, this is a computation which was with the time-dependent Schrödinger equation solved numerically for also photoelectron momentum distributions. You can see here you have this structure which is being reproduced by the Coulomb Volkov approximation fairly well. And here is what you would have with the old theory, and you see that this interference structure is absent, and that the whole thing is starting to fail. But if you go to a lower frequency, where the electrons are going to spend more time in the continuum, and you want to construct this pattern, then you see it starts to get worse. So again, Here, strong field approximation we expect to fail. But if you look at Coulomb Volkov, for instance, here, these fringes, you have 4 fringes. You have many more here. You have all these extra features here, which look like a carpet. I'll come back to that, which you don't have here. And it's not working so well anymore. So people need to go further. Let's try to change the orbits then, which is tougher. So several people then have started to distort the orbits or introduce distortions due to the Coulomb potential approximately or perturbatively. For instance, Sergei Popojenko and Titabawa came up with the Coulomb corrected strong field approximation. So they were expanding the orbits perturbatively around the strong field approximation. Smirnova and Misha Ivanov in Berlin, they came up with the aconal Volkov approximation, which is some kind of laser-dressed WKB approximation. So you have to be away from turning points, and you cannot have huge scattering angles. All these things have some limitations. They work reasonably well. However, one needs to bear in mind that what is being done there is approximate, although not for this one is approximate, this one is perturbative. There are differences there, okay? But I have to make a remark, especially because the audience is coming from quantum chemists, that the aconal Volkov approximation was instrumental and really important for the construction of the analytical R matrix theory. And this is like a normal R matrix theory that you consider the problem divided into spatial regions. So close to the core, if you're dealing, let's say, with a molecule or a system which has multi-electron dynamics, close to the core, you consider the full dynamics, but maybe you don't have to have all the field, because here the dynamics of the potential is dominant. Outside, you consider the aconal Volkov approximation, which is something that you can do because outside you're not going to have huge scattering angles. And you build this for a multi-electron system. And for instance, this is something that has allowed this group to track attosecond hole dynamics in CO2. And this was a milestone in our field because people were pretty much freezing the orbitals. And just even if for you, I know if we talk about orbitals is already an anathema, but you have to consider we have really strong fields here in very extreme conditions. So people were taking like one active orbital, freezing the orbital, and then doing this, and they didn't. They considered such an approach. And this was successful as a means to describing the fact that if you have a molecule with several electrons, you pull one, you're going to create a hole, and this hole is going to migrate. So this is the work if you would like to have a peek. And also one thing that was considered was to treat both the Coulomb potential and the laser field on equal footing. Several methods have done this, okay? So trajectory-based Coulomb SFA by Titabawa and co-workers as well. Path integral strong field approaches, including quantum trajectory Monte Carlo, like a Monte Carlo simulation, but considering that you have trajectories carrying quantum phases, and semi-classical two-step model, and ours as well, which is the Coulomb Quantum-Orbit strong field approximation. And here I put more because I'm going to talk about this in the last 1/3 of the talk. So let's continue. How about this trajectory-based Coulomb SFA from Bauer, Yan, and co-workers? Well, it's nice in the sense that what you're doing is you're solving the full equations of motion in the continuum, and you also have to consider the first part of the dynamics, which is inside the barrier. So for instance, SFA again doesn't work. Here is what you would get from a numerical computation This was done as a benchmark for hydrogen, a very simple model. Here is if you don't have these sub-barrier corrections, you start to see some changes. And here is when they put sub-barrier corrections, because you not only have the propagation and the continuum, you have something that is happening when the electron is tunneling, when it's inside the potential barrier, and you need to consider these corrections. The difficulty they faced was the following, that they had a lot of noise and you have a lot of caustics as well, because the topology of these trajectories are going to change. But so you see here, it's kind of noisy. And what they were doing is they're doing direct propagation. So they were launching tons of trajectories, actually 10 to the 8, 10 to the 9. And they were getting a pattern that we were getting something that was a bit dirty, and they were struggling to switch interferences on and off, because you just beam whatever you're launching in the end. But you have versatility, because you can change your field, launch the trajectories, that's it. But you lose a bit of control. And they found also, and this is very important, that there were more than just the SFA trajectories, and the Coulomb potential changed the dynamics considerably. So these are the people, they solved the problem, both the Viennese and the people from China who did the QTMC, by considering different initial conditions. So they were avoiding all those caustics and all those things that were happening because they had to deal with these dynamics in the classically forbidden region. So they just put some ionization rates, they consider conditions from the SFA. So they were putting them by hand to make it cleaner. And they did get cleaner, but they were again doing this forward trajectory propagation. And you see that the SCTS is slightly better than QMTC, because there were some phases here that they were not taking into consideration. But they're both very powerful, and good things about them is that they are versatile, and here is what you would have in an ambition method. So let's talk about our method. Here is just to give you an example of a timeline and a family tree of all the methods that exist. I just singled a few out to give you an example. And if we move now to our method, what we have done was we started from the exact transition amplitude. Here, this is the full time evolution operator. We didn't iterate, and we used path integral methods to get some expression in which you have intermediate position, intermediate momentum. This looks like a restriction. You also have an action. And the difference is now that when you implement, you are solving saddle point equations like what we had done for the old theory, but with the Coulomb potential. And we were solving a problem that was a boundary problem. We're not launching tons of trajectories. We're asking, given the final momentum, what does my initial momentum have to be? And we had to solve saddle point equations for the intermediate momentum, for the intermediate coordinate, and for the energy conservation and tunneling, but you have binding potential and all sorts of things. So we found 4 types of orbits. These orbits, they have been identified before in this paper with Bauer, Yan, Popujenko, and Rakin, where they had the forward method. But I mean, we were lucky to find them in ours as well, in this boundary method that we used. Orbit 1 is the most boring one. You know, it's reaching the detector directly and is being pulled by the Coulomb potential. Orbits 2 and 3, they are like laser-addressed Kepler hyperbole. If you have potential equal to 0, they merge to a single type of orbit. But the difference is that orbit 3 is also changing because you have this central force. You change the direction of the transverse component of the momentum, transverse to the linearly polarized field. Whereas for orbit 2, you don't have that. Orbit 3 has no strong field approximation counterpart, something hybrid between rescattered and direct. And orbit 4 is something that goes around the core. So it looks a lot like what you would have if you considered that term is Born series with a single vector for scattering. And if you look at how to integrate, we took a contour which is actually very widespread. First we went down, considering you have tunneling, so you went down from a complex time, because we have to solve a complex problem, to the real axis, and then we moved from here to t and took t to infinity. So you have a tunneling part of your action, a propagation part of your action, and in the first arm of the contour, because this is happening very fast and we are keeping the real part of the time constant, we assumed that the momentum didn't change a lot. And with that, we got these expressions. This is what we call tunnel trajectory. The time of the point where the electron leaves, the R naught where the electron leaves for the continuum, we call tunnel exit. And these are sub-barrier corrections that are also incorporated in your method. And in the second arm, we have this expression, and this is associated with the propagation. So we have this term, which looked a lot like the strong field approximation, but bear in mind, this is the intermediate momentum. We have this phase also related to the ionization potential, and we have this term. Note this extra term, which comes from the path integral method. We can calculate this for hydrogen, for the other ones, for effective potentials as well. But this gives you, if you look at our early work where we're doing this for hydrogen, some factor 2. They have also done this separately, and that's why their fringes look okay in comparison with other methods. And we then summed up all these orbits, where here we have what we call the prefactor. Here you have a stability factor, and here you have the CTS, which contains information about the geometry of your initial bound state. We considered linearly polarized monochromatic fields, real orbits after the tunnel axis. This is an approximation. We did also with complex orbits, but then you need to be careful with branch cuts. And as mentioned before, we solved the inverse problem. So given PF, find P naught. And this was an advantage for us. I mean, the disadvantage is it makes the model less flexible. But the advantage is that we don't have to launch a huge number of trajectories. We are going to have actually, for each point in the momentum, in the final momentum that we want to compute, 4 trajectories, which means that you need fewer, much fewer, like orders of magnitude less. And this is also useful because you can switch things on and off. So that's why we decided to use this to understand the physics of quantum interference patterns in photoelectron holography, because we can switch things on and off. So like normal holography, what you're looking at in ultrafast holography is you want to retrieve and reconstruct a target by using phase differences. So you have a probe signal, and then you have a reference signal, and you're going to look at the phase difference between those two, and you're going to reconstruct a target like this image here of this guy. Okay, but what you do with photoelectrons, and photoelectrons are interesting because you have really ultra short time scales and you have high electron currents, is that you're going to use different types of orbits. For instance, you could have a direct and rescattered trajectory, or you could have different types of scattered, or you could have like a hybrid one, like orbits 2 and 3. And we saw that with the Coulomb potential, you have many, many, many more options. And here are some examples of things that people measure in the experiments. For instance, here you can see the spider. These are fringes that occur close to the driving field polarization. This has been measured. This has been computed with the CCSFA, not ours, but by Bauer and co-workers, and you have these huge fringes here. And you have also the fan, which are these fringes that the SFA cannot compute. They have been measured in Heidelberg and in many other places. And we wanted to know how these patterns form. We wanted to know how the Coulomb potential was influencing this. We wanted to know about rescattering, and we had the tools to check this. So this is just to show you what we get, that we have all sorts of patterns. We have fan, we have spider. Here it got better than that afterwards, but we need to take a few things into consideration. But here is an ab initio computation. Here is our method. You can see the fringes work well. You have all these rings, which are from intercycle interference. And let's dissect what is going on, because that's what we could do. Let's start with the fan, which were those fringes close to the threshold, the ionization threshold. There have been in the literature, actually because of the lack of transparency of some methods, different explanations. The people who were using just classical trajectories, or who were using these methods like Coulomb Volkov approximation, they say this is a resonance. So you relate these fringes, these fingers, to a single Legendre polynomial, and you can show that you can associate some kind of angular momentum to them. This was in an indirect way of doing this, but they argued this is a resonance. These people also in Kansas, they have a similar method. They argued, okay, this is also a resonance because you have a well-defined angular momentum. Rostock, they had a method which was more powerful, but they considered then, because they couldn't disentangle the trajectories, that this was the interference between several types of trajectories. And at that time we did this, there was no direct computation of how this forms. So we decided to have a look. Haha. We could see we get the fan. So let's first just add everything and see if we get the fan. We do. It's here. Now, for the strong field approximation, you don't get it. You get completely different number of maxima, and you have some issues. But if you consider the Coulomb Quantum-Orbit strong field approximation, you do get the same number of fringes, and you have some discrepancies here, which now we know is orbit 3. At the time we didn't know, but it's working well. So what is this? What happens is, if you consider orbit 1, which is that one which is being decelerated by the field but is reaching the detector directly, and you consider orbit 2, which is one of the field dressed hyperbole, this orbit, especially orbit 2, is going to be slightly deflected, and this deflection caused by the Coulomb potential is going to be different depending on the angle. So here, close to 90 degrees, this is going to cancel out, and then you can see also here it agrees with the strong field approximation, but here and here and here it won't. So it's going to lead to a divergence, structure. So we could actually say for sure, by switching off all the other processes, is that the fan is due to orbits 1 and 2. The spider, consider the 2 Kepler hyperbole, orbit 2 and 3, and see how they interfere. What you see is you have a spider. You get those fringes that people were observing, and you get, this is without the prefactor. This is in fact a big caustic. You put the prefactor, it goes much more down to the polarization axis when you look at this photoelectron momentum distribution. And we also predicted a lot more, in fact, patterns involving orbit 4, which we call the spirals. And there were many more spiders and many more spirals and fans that people thought, just because of the presence of the Coulomb potential. And with the spiral, it's an interesting case, because what is happening is that this was a case of mistaken identity because of the old theory. Remember at the very beginning of the talk, I showed you a picture from 2012 in which people showed interference carpet. So you have these rings. They are due to intercycle interference. And if you look here, perpendicular to the polarization axis, you see that you have a spacing, you have a separation of 2 omega. And people always thought, okay, I can predict and I can use the strong field approximation here because the Coulomb effects are going to get canceled out. And they said, this structure doesn't come from anything involving any interaction with the core, because this can be modeled by using the long and short, which are 2 orbits that come from the strong field approximation, but in its direct version. Now, we realized it wasn't the case. We realized that you would have, if you this is for a specific type of initial conditions, but if you superpose 2 orbits, one which is identified as orbit 3, this Kepler hyperbole, and this one which looks like orbit 4, and you add them coherently, their contributions coherently, you see that you're going to get a lot of spiral-like structures. And this, if you superimpose, depending on the initial conditions that you have, are going to lead to the carpet. And this is kind of useful because you see, this is being distorted by the core a lot, is going around it. This is a field dress hyperbole, and the core makes it the momentum perpendicular to the field change sign. So for holography, what do you want? You want really, if you want to probe a target, you really want contributions that interact with that target. And you see that this carpet is very clear. So people in Wuhan then measured this. We explained it, got into a lot of trouble, to be honest, but this is the experiment. We plotted here just to eliminate those rings. We plotted this in terms of energy and scatter versus scattering angle. Here you can see 90 degrees, you get those features. They also get this. And what was interesting here is that the spider occupies a totally different region, which is the one close to the polarization axis. So this here and this here would be the region occupied by the spider. Spider is quite strong. So if you have something that occurs in a region where the spider is not prominent, this is nice. Okay. Now, we decided just to be sure to check all other combinations of orbits. So we had the experiment, we had our computation using everything. And here we just consider the interference between orbits 3 and 4. Matches the experiment really well. Now, if you consider the old theory with orbit 1 and 2, you have a carpet, but it's a different carpet. In fact, we realized that direct strong field approximation, rescattered strong field approximation, orbits 1 and 2 with Coulomb potential, and all the orbits, they were leading to carpets, but this is associated with the symmetry of the field. This had nothing to do with the process, that you needed to look at the vicinity and the energy range to be able to say if you had the right carpet, because in one case you had, let's say, a Persian carpet, in the other case you had a Coulomb, in the other case you had, so depends on what type of carpet you are measuring. And depending on the carpet, you're going to have a different physical process that before wasn't identified because of the presence of the Coulomb potential. So this was nice, and let's look for applications. And a very nice application is to explore holographic structures to detect the parity of molecular orbitals. So let's say you have a molecule, and let's say you have an atom, and let's say that they have different parities, this highest occupied molecular orbital and your atomic orbital, and you can orient them like a p state. You know that depending on how things go in the continuum, there are going to be phases that are accumulated. First, you're going to have a phase that is coming from the bound state, and you're going to have a phase that is accumulated in the continuum when the electron is propagating. For instance, here we have orbits 2 and 3 leaving from this opposite side of your detector. They lead to the spider. Here you have orbit 1 and 2. 1 goes directly to the detector, 2 leaves from the other side. So you have a difference in the path that is going to pick up some phases depending on whether your target is even or odd. And you have also 3 and 4, where 4 goes all the way, and 3 is a field dress hyperbole, which leads to here in this direction to this transverse direction to this carpet, which you have established in the previous case. So you're accumulating a phase due to the bound state and due to the continuum. And what we have done was we took atoms and molecules with similar ionization potentials because we wanted the phases accumulated in the continuum to be similar. And this is something that was important for us because if you have different phases in the continuum, it can happen if the ionization potentials are too different. You have to take them into consideration as well. Don't forget, it's not only the field, you have the Coulomb potential. You're going to have a different point in space which with this electron is reaching the continuum. You have a potential barrier that is changing. So you would like these phases to be as similar as possible. So if you want to do some probing of parity of orbitals, you want to pick up a molecule and an atom which have a similar ionization potential. Also, you would like to have different phases being picked up from bound states. So for instance, for the fan, where you have orbits 1 and 2, there's going to be a phase difference of pi if you have even, if it comes from an even bound state or an odd bound state, because one just went directly to the detector, the other had to come from the other side. And this is going to lead to lead phase differences depending on how things are being crossed, like what changes happen spatially. For the spider, they're coming from the same side. They're just these 2 Kepler hyperboles, so it doesn't really matter. For the carpet, it's going to matter because again, orbit 1, or not orbit 1, orbit 3 is like laser dress Kepler hyperbole. Orbit 4 goes all the way around it. So they're coming from different sides, and this is going to play a role. So just to summarize, if they come from opposite sides, they're going to be shifts. If they come from the same size, there is no shift. Okay. If you look, so this is what they measured in Frankfurt. We took argon and N2 because N2 has 3 sigma G as a HOMO, and argon has 3p, and they have more or less the same ionization potential. So we are sure that in this case, you had an even orbital situation. Here you had an odd one. This is the measurement that was made experimentally. You can see you have this carpet. Here you can also see very clearly. This was a simulation using the time-dependent Schrödinger equation with an effective potential. You also see this. And this was computation used with CQ SFA. So you can see here that you have the fan, that you have the spider everywhere, and then here you have the carpet. So we decided to use the carpet because it was the clearest one. And if you are close to here, to the fan, although you know from what interference they come, you still may have, depending on whether you have a multi-electron system, multi-electron effects that you may need to take into consideration. So yeah, we normalize the spectra, we added, we subtract them, and we normalize this difference, and we could see actually that the carpet was swapped. As expected, there was a phase difference of pi, where you had a maximum for argon, you had a minimum for N2, and the other way around, both in experiment and in the CQ SFA using orbits 3 and 4. So it was quite nice, and we were happy about it. And we realized that you can go beyond. You can talk about multi-path interference, because so far there has been the focus on interference between two types of paths, 1 and 2, 3 and 4, etc. But how about the situation in which you have, for instance, a modulation in the spider legs, which is something that you can see here. So this is something that has been computed, and this is a measurements as well. This was done in collaboration with the group in Stanford and a few bound groups. And we said, okay, if you have a bound state and if you have no bound state, because we're considering argon, you're going to have a phase shift in the carpet, you're going to have a phase shift in the fan. You don't expect to have a phase shift in the spider. But if the modulation on the spider is coming from the fan, which is the case, then you're going to have a phase shift. So if you look at the filtered experiment, and if you look at what you get from the theory, you expect to have pi phase shifts between orbits 1 and 2 and orbits 1 and 3, and it shows. Here I was talking about the carpet, but we can have a look at this. So these lines are the computations with bound state and without bound state, and then you can see also what you have from the experiments, and you really see that you have these phase shifts, and when you include the bound state, you start to have an agreement. The interference maximum and minimum match. So you don't need to use a specific holographic feature that you see in these momentum maps in a region which you are safe, because maybe the other ones are absent, like the carpet. But you can use also multipath interference. You can use modulations on holographic structures like the spider, which is very, very, very strong, both in theory, experiment, whatever you do. I mean, many people have struggled to get rid of the spider because it's very strong, but you can use modulations in the spider which come from other type of interference. And they do agree if you include. We included other things as well, but they do agree. So just to summarize my talk, we're well in time. I wasn't sure how much time we should have for discussions and how much time we should have for the talk. But just to summarize, I mean, the key message, I've talked about the old theory, I've talked about the new theories that exist. I talked a bit about my field. The key message that people should really take home is that the old theory that was the backbone of my field, and it still is to a great extent, which is the strong field approximation, is really, really, really powerful. But the residual binding potential is important. And even if it's important, I mean, look, the examples I showed from our own work, they were done for very simple systems. And just to have that Coulomb tail, or if you have an effective potential for something else, has already changed a lot of the dynamics. Imagine now that you have a big system with many degrees of freedom, and it gets more and more difficult to distinguish between bound, continuum, and other things. And because we're talking about quantum interference, we need to be really aware that this is going to change the phases that each quantum pathway is going to pick up. And that's why we wrote a review article recently, and that's why we decided to call it It's All About Phases, because we realized it is. Really, if you're looking at ultra-fast holographic imaging, and if you're really looking at how to deal with this kind of situation, you need to be aware that phases are going to be super important, phase differences between one quantum process and the other. So yes, it's all about phases. And last but not least, I'll close my talk, and I would like to thank a lot of the people who have left, who have joined, our collaborators, and we're going now in the direction of really multi-electron, tailored fields, and other things. So I would like to thank Abby Bray, Andrew Maxwell, Heloise Chomet. She's doing something else, looking at Wigner functions and things like that. Cornelia, Gyung-hoon, and Tom are looking at tailored fields. Lydia, Sophia, and Brad, we're looking now at multi-electron Coulomb Quantum-Orbit strong field approximation. Not ready to go public, but we hope we'll be soon. Thanks to all our collaborators, and of course the funding agencies, because although money can't buy you love, it's still important to do research. Thank you. And if you are more interested in our area, do join our Auto Friday seminar series. They take place at 3 p.m. London time. Registration is free. These are for people who registered for the Quantum Battles in Auto Science, which was a conference we had in 2020 about courting controversy online, which was also great fun. But if you want to join and you want to check the talks, do have a look at our program. We also have a YouTube channel, or follow us on Twitter, or drop us an email at Quantum Battles, but please not too much spam, okay? Just keep it simple. And finally, I would like to thank your attention.
Okay, thank you, Carla, for this interesting talk. I think this is very much outside of my expertise, but let's see if someone from audience have any questions. So you can write them in chat, or you can raise your hand, and then we can.
There seems to be something in the chat.
No, that's just me telling them to.
Okay.
To ask. Actually, maybe someone wrote a question directly to you. That I don't.
Let me have a look. I don't. No, I don't. Because you have this other platform, right?
No. So, yeah, I don't. So I need kind of. I don't really know if I understood everything what you were talking about, but. Because you were talking now about this, you have 1, 2, 3, 4 these orbits, but mostly you were combining then 2 of them, because you said you can turn on and off.
Yes, I mean, because our issue was to understand, okay, in the sense that people were finding all kinds of patterns, nobody knew where they came from. And we wanted to understand the patterns and then use them. So that's why when we developed our theory, we considered something that is more difficult to solve numerically, because you don't have many trajectories 10 to the 8, 10 to the 9 that you launch, but you have something targeted where you ask, okay, given these conditions, and given this final momentum and these conditions at the end of the first part of the contour, the complex contour that I was showing you, what do I have to have in between to satisfy these conditions and have this type of orbit? So it's more technically it's much more difficult. And also this is the advantage of our method, that it makes it less flexible. But we wanted to understand where those features come from. Because if you want to probe a system and you see that the photoelectrons that are being emitted by that system in a strong field lead to specific patterns, and these patterns are associated with several types of quantum interference which are superimposed, you need to have tools to be able to disentangle what types you have. And that was our key objective, because what we had was the old theory, which is very powerful, but cannot account for even the simplest type of structured continuum, which is with a Coulomb tail. Okay. Or you have a lot of methods that incorporate what you want, but that sometimes operate like black boxes, that you have like a numeric experiment, and it's very difficult then to reconstruct what is going on. So our objective was, okay, let's then treat the potential and the field on equal footing. Let's consider that we may have all these types of interference, and let's try to disentangle them. And then once we have understood them, use them as tools, for instance, to measure parity. Okay.
Yeah.
Yeah, I mean, I don't know, because we are struggling to do this for more complicated systems. We are trying, okay. We're not ready to go public, but we are aware that you know, it's sometimes it's not only about reproducing what is in the experiment, it's understanding in depth what is going on.
Yes, that I agree. I think sometimes we want also to actually understand why and what, you know, because then you can kind of maybe give suggestions for something else, for a new experiments and things. But what is the most complicated system which you have looked at?
Me, so far diatomics, triatomics, okay? But if you talk in general, people in my field are looking at organic molecules and solids. But it's like this, either you use some hybrid method where you bring some elements of a quantum chemistry package, or you develop your own quantum chemistry method and then you mix up with strong field, like this ARM. Now we have some questions in the chat, it's good. Or you use you try to come up with stuff from scratch. The difficulty is not the system, because I understand that in general, if you're not working with strong fields, for you guys the difficulty is the target. Okay, for us difficulty is the field, and now it's becoming also the target, because all the stuff that you use because of the extreme conditions is going to be invalid. Okay, yeah. For instance, we have a question here. Is perturbation theory the only way to incorporate the effect of the external field? No, it's not. Thank you for your question, Songao. Because it's not, and that is exactly the point. This field is so strong that if you try to use perturbation theory, you're going to fail miserably, because this is what people tried to do in the 1990s, 1980s. And that's what is making difficult. And you are asking about quantum chemistry techniques. You can mix and match. You cannot pick up quantum chemistry techniques and use them blindly in this field. For instance, if you're curious, you can look at the work by Fernando Martin and Alicia Palacios, who are like pioneers in quantum chemistry, where you can mix and match. You can use, for instance, numerical techniques that are used in quantum chemistry if you're in a region where the potential is dominant, like close to the core, but you're going to have a boundary which you need to match with when you are in regions where the field is dominant. And that's why the Berlin group, Sergei Pachkovsky, August Mianova, and Misha Ivanov, develop this analytical time-dependent R matrix, because it was a bit of doing mix and matching using standard quantum chemistry techniques in a region where they could, but then moving away from it and having Coulomb corrected, in that case wasn't fully Coulomb distorted methods in a region where the field is dominant for multi-electron system. And hi, Professor, thank you for your talk. I would like to ask, how do you choose the wavelength for the laser? We tried everything, but one thing that is important, one thing that is important for us is that we are in the tunneling regime, okay? So we have done simulations for 800 nanometers. We have done simulation for also much longer wavelengths, like mid-IR and so on. But the important thing for us is that tunneling is the prevalent mechanism, because otherwise you would have to consider much more the effect of resonances and the effect of things that do not involve only a bound state and a modified continuum, because we made some assumptions when developing our theory that doesn't deal with resonances very well unless you have a very highly excited state. And Songao is asking, like, coupled cluster Green's function. I don't know coupled cluster Green's function. Can you explain? I mean, I'm not a quantum chemist, but yeah, we do play around with Green functions. And I just don't know.
So I also have a relatively shallow understanding, but it's actually a PhD thesis of my supervisor. And basically, it's just a use exponential ansatz to parameterize the Green's function, and which is not based on perturbation theory. You know, coupled cluster in general is a non-perturbation theory.
Okay, I don't know the method. I would be grateful if you could send me the reference. One thing, if you're not using perturbation theory, that you always have to be careful with is because many people, they use stuff which is non-perturbative but is adiabatic. Can you consider that your dynamics changes slowly so that you can make some assumptions? This is the first question. I don't know this method. This is the first time I'm listening to it, and that's why it's good to give talks in a different area, because you always learn new stuff. I would appreciate if you could drop me an email with the reference. It's always good to have a look. Or even put in the chat right now, I think is good. And I don't know, I mean, we're not assuming, I mean, we have exponential things that come from our propagators, okay? And from our time evolution operators. So in this sense, it's a bit like Green's functions. But we have also things that are highly oscillating. And you need to be careful with that when you treat, for instance, to solve, I mean, actually these saddle point method that has been being implemented for a long time in the SFA and is actually quite useful, came at the beginning out of the necessity. Now we know how to integrate these oscillating functions numerically. But we don't really know, or at the beginning, we didn't know how to do that integration. So we went for asymptotic expansions. It turned out that for at least my specific purposes, asymptotic expansions are more useful because I can then understand what is going on. And it's easier also if you need to extend this for like larger systems, because numerically is less expensive. It's just mathematically is more complicated. Dominica Skid, I don't know this person, but coupled Green's function, okay, I think it helps. You see, coupled cluster Green's function, Dominica Skid. Thank you so much. I think it helps. Definitely doing it.
Zonghao, you can also write it on the web page. you can write there a comment. I think that's also one way how you can contact the speaker. So I want to ask if there are any more questions. Anyone else wants to ask something? Just raise your hand. If that is not the case, I would like to thank you, Carla, again. This was very interesting, and I think people enjoyed it because it's very different from what we heard in the other talks during the winter school. And yeah, if nobody has anything else to ask, thank you again. I will stop recording.
Thank you.